All right, folks, this is our last kind of problem that we're going to go over with related rates. Are there lots of other possibilities? There sure are, and maybe someday I'll add a few more videos onto this collection of examples of related rates problems. But this is as far as I'm going to go right now. This is what I call the conical water tank example, or the conical water tank problem, and I'm going to do two examples. This is the first one. And the idea is that you have a cone-shaped water tank, and it's usually turned upside down, kind of like those little cone-shaped water cups. And you either have water that's being poured into it, or the water is coming out of it, like maybe it's dripping out of the bottom. Either way is fine. So let's go ahead and read the problem here. It says, water is pouring into an inverted cone-shaped water tank. The cone is inverted, meaning a cone is turned upside down. Okay, kind of like the way you hold an ice cream cone, right? And the water is pouring into the cone at 60 cubic centimeters per second. Okay, water is pouring in as measured, in this case, measured by volume. The height of the tank is 100 centimeters. That means from the peak down here, the altitude, from the distance from down here at a 90-degree angle up to the top of, or the base of the cone is 100 centimeters. And the radius of the base, now I know that it's upside down, so you might have a hard time thinking of this as the base, but the largest circle at the bottom of a cone, that's called the base of the cone. And the radius of that circle is 25, okay? And now the question is, at what rate is the water level of the tank rising? Because the water, here's the water in the tank, it's rising as water pours in, right? At what rate is the water level of the tank rising when the water is 20 centimeters deep? So this 20 centimeters is not constant. It's actually, the water level is going higher and higher. So it's going to go from 20 to 21 to 22 to 23. And it can only go as high as 100. Okay? So here's what you need to understand in order to do this problem. The first thing I want you to get, I want you to understand that I want to penetrate your skull is this. Do you see the water right here, this blue area? That's the water in the cone. The water itself is another cone. We're actually dealing with two cones here. There's the cone that's the tank, and then there's the cone that's the water itself. And what you need to understand is the tank itself is not changing. The tank is not changing. The tank is a fixed size. But the cone of water that is in the tank is changing. It is getting larger and larger as water pours in. So really, the cone we're going to be dealing with here is not the cone of the water tank. We're going to be dealing with the cone of water that is in the tank. And the reason that the water is taking on a cone shape is because it is in a container that is cone-shaped. And that's what water does. Water takes on the shape of whatever container it is in because water is liquid. Okay, so here's what we got. We're going to start with identify the given rates. Okay, well, here's the thing is, let's go ahead and look at this. Water is pouring into an inverted cone-shaped water tank at the rate of 60 centimeters cubed per second. That's a volume. And so what we're given here, the first thing we're going to identify, the rate of change we're given is the rate of change in volume. dV dt is 60 centimeters cubed per second. That's the only rate of change that we're given. Identify the unknown rate. It says at what rate is the water level of the tank rising? So it's not the tank that's changing, it's the water level that's changing. The amount of water is changing. And that is, what is the water level? Doesn't it start out down here, and then as it fills up, it goes higher and higher? H, higher, height. It's the height that's changing. So what we're trying to find here is we're trying to find the rate of change in the height of the water cone. So we're trying to find dH dt for the water cone, okay? The height of the water. When the water is 20 centimeters deep in the tank. Now, we need a formula that relates volume to height. Okay, so volume of a cone related to the height of a cone. Well, here's what you can ask. Start by asking, is there a formula for? Is there a formula for the height of a cone? Not really. I mean, there could be one in special circumstances, but the next question is there a formula for the volume of a cone? You bet there is, and guess what that formula includes? The formula for the volume of a cone includes height as one of its variables. So we're going to use the formula for the volume of a cone. Now, you may not know what that formula is, so I recommend that when you don't know what a formula is, you get your phone out or get your computer out and look it up on the internet. You can find the formulas for almost any regular geometric shape. The volume of a cone, I happen to know, is 1/3 times pi r squared, which is the base of the cone, times height. So 1/3 pi r squared height. All right, that's the volume of a right angle cone, I guess is one way of saying it. Okay. All right. So look, now that we have the volume, now here's the thing. It says we're going to plug in for all constants. Well, the volume is changing and the height is changing, and actually the radius is also changing. Think of what happens as this water cone gets larger and larger. As the water fills up, what's going to happen to the radius of that circle? It's going to get larger and larger. So all three of these variables are changing. But here's where I want to stop for a second. And I want you to think back to the lamp post problem. There's something that we can do here, something that we must do here in order to make this problem a little bit easier. We are going to relate height and radius to each other so that we can eliminate radius. We don't want to deal in radius here. But look at this. Do you see this cone? And this is the key to understanding. Remember in the lamppost problem, we had two similar triangles? Well, in this problem, we have two similar cones. This water cone is similar. It has all the same dimensions, proportional dimensions, as the larger cone because the water is filling the tank. And so this cone has the same proportions as this cone. So we want to identify the relation of the radius to the height. So how is radius? Hang on a second here. I think I want to put the height. Well, it doesn't really matter. At least I don't think it does. We're going to do radius over height. And in this case, the proportion of radius to height is radius is 25 and height is 100. And this makes it really easy now because 25 over 100 is 1/4. 1/4. And so the proportion of radius to height, since it's 1/4, what we can do is we can solve for radius. Why are we solving for radius if we want height? Well, we're solving for radius because we want to get rid of radius. The variable you want to get rid of, you solve for it and then substitute that into your formula. Let me show you. Let's do it and it'll make sense. To solve for radius here, I have to multiply both sides by height. And so now what I get is radius is equal to height over 4, or 1/4 of height. And now I can come over to my volume formula, and I can say volume is equal to 1/3 times pi. And instead of putting radius, I can put what radius is equal to. Radius is equal to height over 4. So I'll put height over 4 squared times height. And now all I have to do is clean this up. Okay, so to clean this up, this is going to become, volume equals 1/3 pi, and then height over 4 squared, I have to square height and I have to square the 4. So I'll get height squared over 16 times height. Well, height squared times height is height to the 3rd power. So this is h to the 3rd power. And this can be cleaned up even more here. I can put the pi with the height, or I can do the 1/3 times the 16 here. Basically what it becomes is 1 over 48, because I'm doing the 1/3 times 1/16, pi times h to the third power. And I can even put the pi up in the numerator because pi times 1 is pi. And so now my final formula, my volume formula, is now pi over 48 times height to the third power. Now I can do step 5. I can do the derivative of this. In step 5, the derivative, dv dt, is equal to, I'm going to multiply this 3 times pi over 48, because I'm doing a derivative, this times this, and then reduce the power by 1. So I'll get 3 pi over 48 h squared, because I got to reduce the power by 1. Then I have to put the dh dt on, because I'm doing the derivative of h with respect to t. That is now my formula, right? And now I can do step 6 where I plug in. I was told what dv dt is, which is 60, equals 3 pi over 48. That's a 3. 3 pi over 48. H squared. Well, h, when the water is 20 centimeters deep, depth is the same thing as height. Depth and height are the same thing. So 20 centimeters height, 20 centimeters deep, squared times dh dt. And dh dt is what I'm trying to solve for. If I clean this up now, I get 400 times 3 pi, and that is 1,200 pi over 48, 60, and dh dt. And now, to get dh dt by itself, I can multiply both sides by 48 over 1,200 pi. I do the reciprocal. If I multiply by the reciprocal, it cancels. So I'm going to do 48 over 1,200 pi, and that's going to cancel 48 over 1,200 pi, and 48 times 60 is 2,880, so 2,880 over 1,200 pi equals dh dt. And I'm going to go ahead and get a value there. So I'm going to divide this by 1,200 pi, and I get 0, dh dt is equal to 0.7639 centimeters, because height is a first dimensional variable. It's a distance. So I'm not going to put centimeters cubed. I'm putting centimeters per second. This is my rate of change in the height of the water. You can see why I did this one last, right? These are pretty tough. These can be pretty tough. You gotta really think about them. But here's what I recommend you do. If you're working on a problem that is similar to the conical water tank, then have this video up on your computer where I'm explaining it. Work through your problem and watch this video over and over. Not the whole thing, but maybe just the pieces, so that you can relate your problem to this problem. I am going to do one more example of the conical water tank. Interestingly enough, it's not a cone, it's a different shape, but it's still basically a water tank, and it still uses the idea that I have to relate two variables to each other because I have similar shapes. One shape that is water, and the other one that is the container that the water is in. Okay, so let's go ahead and do that one. All right, folks, here's the second example for the conical water tank, only this time it is a triangular prism, like a trough, okay? Something you'd put water in that animals would drink the water out of, okay? And here's what's happening is, in this situation, the water is actually being removed from the trough. It's being pumped out of the trough. This is a trough in the shape of an inverted triangle. That means the triangle is upside down. Triangular, sorry. A trough in the shape of an inverted triangular prism is 5 feet long with a base of 2 feet. So that means the base is 2 feet and a height of 3 feet. So this is actually, I didn't clarify on there, this is an isosceles triangle. And so the height of the triangle is 3 feet, and the base of the triangle is 2 feet, and the length of the prism is 5 feet. Okay? water is being pumped out of the trough at the rate of 2 cubic feet per minute. And at what rate is the height of the water level changing when the water is 1 foot deep? So when there's only 1 foot of water in the trough. Okay. So here's the thing: we have to do the same thing that we did with the conical water tank. We have to remember, there are 2 triangular prisms here. There's the trough, and the trough is not changing. It's not changing shape at all. But the water inside of the trough is changing. It's changing shape because the water level is going down. And so this triangular prism is getting smaller and smaller and smaller and smaller. And so the volume of the water is changing, the height of the shape is changing, and because it's a triangle, as it gets smaller and smaller, the base of the triangle is getting smaller and smaller. So the only thing that's not changing about this triangular prism of water is that it remains 5 feet long. So it's always 5 feet long. Okay? So let's go ahead and identify the given rates. Well, we're only given one rate of change. We're told that the water is being pumped out at the rate of 2 cubic feet per minute. And that's a volume thing. Okay, so the rate of change in volume, dV dt, is going to be equal to -2 because it's being pumped out. Step 2, we're going to identify the unknown rate. It says at what rate is the height of the water level changing? So that's the height of the water shape. And so that's dH. dt is what we're trying to find out for the water shape. The height of the trough is not changing at all. The height of the water is changing. So now we got to identify a formula that relates them. Well, the volume of a triangular prism is the area of the triangle at the end, the area of a triangle times the length of the prism. Well, the area of a triangle, so volume is equal to, the area of the triangle is 1/2 base times height times length. Times length. Base times height times length. But we now, remember what we did in the conical one? We have 2 similar shapes. Both of these prisms are similar. They have similar proportions. In particular, the base and the height are proportional to each other. So in this, the base is 2 and the height is 3. Now we want to keep the height because the question is asking about the height. So we want to solve for base. We want to relate these 2 things to each other. So we could say that base over height is equal to 2/3. And now if we multiply by height on both sides, it's going to cancel height on this side, and base is equal to 2/3 of height. So we're going to come down here to this formula, and we're actually going to go to step 4. And in step 4, we're going to say volume is equal to 1/2 base. We're going to replace base with 2/3 height. 2/3 height. We're going to leave the h. And then length. Remember how we said the length is not changing. The length is constant. So we're going to plug in for constants, and the length of this prism is 5 feet. Even the water prism has a length of 5 feet. So we're going to put a 5 here. Let's clean this up a little bit. 5 times 1/2 is 5/2 times 2/3 is equal to 10/6. Now I could have just canceled these 2 2's, right? And gotten 5/3. So this times this times this, and then my h's, h times h, that's h squared. And so now my real formula is volume is equal to 5/3 h squared. Okay? That's just when I clean everything up. I would encourage you to do that on a separate sheet of paper if you're not sure, if you didn't follow along with what I just did. Okay? All I did was 1/2 times 2/3 times 5, and then h times h. H times h is h squared. 1/2 times 2/3 times 5 is 5/3. And so now I can do step 5 where I do the derivative. Now that's a piece of cake because this is now a very easy formula. The derivative of v is dv dt equals 5/3 h squared. So I got to do 2 times 5/3 gives me 10/3 of h, and then my power has to go down by 1. So I got to go down from 2 down to 1. So it's h to the first power. Then I got to throw on my dh dt. So this is my derivative. That's step 5. Step 6, plug in given and implied values. Well, everything here is given. dv dt is -2. I'm going to put that here. And then the question says, what's the rate of change in the height when the water is 1 foot deep? That means the height of the water is 1. So in for h, I'm going to put a 1. So step 6, for dv dt, I'm going to put in -2 equals 10/3 times 1 times dh dt. Clean it up a little, and I get -2 is equal to 10/3 dh dt. To cancel 10/3, I multiply by 3/10. Multiply by 3/10 on both sides. That'll cancel this, and all I have left over here is dh dt. 3/10 times -2 is -6/10, which reduces to -3/5, which is also -0.6. And I will put, now we're dealing in height. Height is a first dimension variable, so we're not going to put cubic feet, we're just going to put feet. Feet per minute. Feet per minute. So dh dt, the height is decreasing, because I got a negative, the height is decreasing at 3/5 feet per minute, or 0.6 feet per minute. And there's our last example for related rates. Hopefully you feel a little more like a pro now that we've done so many examples, and now you should do just fine on any kind of problem, related rates problem that you face. Okay? All right, well, have a great day.